So now that we have copied our sphere to all of the points generated by our very small distribution network, let's go ahead and turn our attention to the animation part of this crowd simulation. Now, as far as animation goes, all our audience is going to do is squash and stretch. But we need to make sure that the squash and stretch is unique across all characters. This is very important. If we don't do this, we're going to have a very uniform motion taking place, and it's not going to look like a natural crowd. These guys need to look as if they are thinking on their own. Some are a little less excited, some are much more excited, and by having some jumping higher, some stretching more, some squashing more, etc., and some barely squashing and stretching at all, we can give that feel. Now, if you recall, our crowd is being generated from a single node, our audience sphere node that we put down. If we were to take that node and run it through a simple twist SOP, that would give us the ability to squash and stretch this node before it gets duplicated. Now, if we drive the strength on the twist node, basically how much are we going to squash or stretch our geometry, and in driving that we use information that's being stamped back up from our copy that copies the sphere to all of our points, we can generate unique values for each sphere, and that's where things are going to become quite powerful. So let's go ahead and jump over to the whiteboard and spend just a minute talking about some of the parameters that Steve will be creating in this video, as well as the expression that we're going to be using. So first thing, let's go ahead and create a new layer. I'm going to go ahead and scroll up so I have a lot of room to work with. So we know right now that we've got a sphere, and that data is being passed on to, well, basically to where it's going to get copied around and all. But what if we were to come in here and pass it into a twist, and we set the operation on that twist to a squash and stretch, and now how do we drive the strength of the squash and stretch? Because by default, if we squash and stretch right now with the strength, we're going to see everybody stretch the same amount and everybody squash the same amount. What Steve is going to use is going to be an S-noise expression. And the S-noise expression generates 3D noise. And the interesting thing about this noise is while it's random, it's not really random, because if you were to go from any point in the 3D space that's generated over to another point, it's going to flow. So basically, if one point is sitting in space and we were to go to the point right next to it, we would not end up with some really crazy value like this. I mean, this would be, so let's say we went over and the next value was there, and then we went over one more and the next value was way up here. This would be a very randomized look. Instead, what we're going to get is going to be, and I'm just drawing this kind of in 2D space right now, but remember, this is a 3D noise. But you'll see here, we're generating something that's nice and smooth. And this is very important, because otherwise, if it was truly random, what you would end up with would be on one frame, a sphere that was completely squashed, and the next frame, that sphere could be completely stretched with no interpolation taking place in between, and it will end up looking like a bunch of pops.
Yeah, we just get flickering and popping. It wouldn't look like a natural animation.
So S-noise is going to work wonderfully for us. So S-noise takes in 3 parameters. Basically, we can give it an X, a Y, and a Z. And we're going to use all 3 parameters to represent something different so that we are able to more or less move through the 3D noise for every sphere that we have, which will generate a different series of numbers.
Exactly. The 3 parameters can be thought of as X, Y, and Z, with each being a different direction that we're traveling through our 3D noise. So if we change along the X-axis, we're going to be moving through that 3D noise. We're going to get a change, some form of smooth randomized curve like Jason just drew on the whiteboard. The same is true if we move on Y, the same is true if we move on Z. So if we use a combination of these 3 axes and drive each with different values, we can have different values affecting our 3D noise.
Very good. So let me do this. I'm just going to break apart the spaces for our X, Y, and Z. So the first thing we're going to do for our X component is we're going to set this up so that we have some sort of changing value over time. So val changes over time. As far as Y goes, this needs to be a unique ID. This is very important for the simple fact that we want to make sure that every single sphere has a unique value once again in this world of 3D space, be it us moving in X, Y, or in Z. But this changing value right here, this guy's not going to be unique to every single sphere. It's going to be shared amongst every single sphere. So by having a unique value put right here, now everybody is still sampling off a different space in that 3D space in which we're generating our numbers from. And then finally, we're going to put one more value out here that's going to allow the artist to control a seed so that he can shift everybody around until he finds the exact motion he's looking for this crowd. So for our changing value over time, we're going to create a new parameter up on the asset called noise speed. And for abbreviation purposes, I'm going to call it NSPD. If we were to take NSPD and multiply this by the current frame number, when you hit play, then of course the frame number is going to be changing continuously. That's going to give us a value that changes over time. So we can use $F to gain access to the current frame number. Now for our unique ID, this one's going to be real simple. Let's just jump down to the copy, where we're taking the sphere and copying it to all of the points that have been created by our distribution network, and let's simply stamp up some sort of ID. And we can just grab the $PT, the point number that we're copying that sphere to, and stamp that information back up. So we'll call that stamped variable something like sphere none. And finally, for the seed, this is where things get very easy. We simply come back up to our asset and create a noise seed custom parameter. So noise seed, not to be confused with noise speed. Let's call this guy NSD. And so we'll simply put NSD in the final, as the final argument. So NSD. There we go. Now, if you were to open up Houdini's help file and take a look at S-Noise to see what kind of data is returned, it's approximately, using their language, a value between negative 1.15 to a positive 1.15. Now, our strength is going to, once again, need to be set up or controlled by an artist. So we're going to give our artist a couple more parameters that will allow him to affect the minimum amplitude, meaning just, well, minimum and maximum.
Yeah.
Trying to break
so
that down.
How far can we squash down and how far can we stretch out? And that's going to basically be two different strength values that we are allowed to set as an upper bound and a lower bound. And we're going to remap S-Noise, which returns between around negative 1.15, positive 1.15, remap that to our new minimum and maximum amplitudes.
Very good. So for a second, it just blew my mind. I was like, well, I'm starting to break down min-max. Why am I doing this? But you did a good job of breaking it down. Okay, so we need to basically remap this returned value between the minimum and the maximum. Now, we've used fit01. I don't know if we've used fit in this particular project.
I don't think we have.
I don't think so either. Fit allows us to specify an old minimum and an old maximum, where fit01 assumes that the old min's 0 and the old max is 1. So we'll simply say fit, and then inside fit, we're going to put our value that we're remapping. That's the result of our S-Noise. So I'm just going to put S-Noise right here. And we know everything up above is in there. So this line right here is this guy right here. And now I need to put a comma, and our next argument is going to be, what's the old minimum? Well, we know that the value that could be returned, the lowest value that could be returned from S-Noise is approximately negative 1.15, comma, our old maximum. Well, the most that could be returned out of S-Noise is approximately 1.15. Now, what are we going to remap the value to? Well, we're just going to remap it between our minimum amplitude and our maximum amplitude. So for our new min, we're going to put min A. Now remember, min A is this guy right here. And then finally, max A. Let me just kind of jump down for just a second. So this is for those that are new to this. Value being remapped. This right here is our old min. This is our old max. This guy is our new min. And this guy is our new max. And with these two custom parameters, the artist has full control over just how much they can stretch, how far down they can squash. Now there's one more parameter that we're going to add in that's going to allow an artist one extra level of control so that he could start scaling the animation down all the way down to 0. And if we want to, we can basically turn it off with that. This is going to be an overall control. So if we come up here and add one more custom parameter, overall control.
This is going to be really useful because we may be in a situation where we want our audience to kind of be excited but not greatly excited.
Or to start ramping up.
And then ramp up as something exciting happens. So we could start, say, around 70% and then push it to 100%, and then we could drop that back down to 0 if the audience have settled and they're no longer excited over the performance.
And to do this, we simply create the overall control custom parameter, multiply our remapped value by our overall control. So when overall control is a value of 1, then we have this remapped value, full value, being applied to every single squash and stretch strength value. If this is 0, then we would have nothing applied, because 0 multiplied by any number is always 0. And then if it's somewhere in between 0 and 1, then we'll have a ramping up amount of animation as we get closer and closer to a value of 1. So this is what we're going to set up in this video, and this is going to give us the unique looking squash and stretch animation applied to all of our spheres. So Steve, you ready to hook this guy up?
Yeah.
All right.
Alright, so now that we're over in Houdini, we're going to be focusing on this area of the network here, where we've got our sphere geometry being copied to our template points. And before we've generated our, after we generated our sphere, before we copy the sphere around, we want to apply our animation, and we're going to do that with a twist sop. So I'm going to right click on the output of the audience sphere and create a twist sop. Enter to accept that, enter to drop that into our network. Let's give ourselves a little bit of space. I'm going to rename this guy to audience, squash, and stretch. And let's bring our visibility down here so that we can set up our basic parameters on the one sphere, and then we'll take a look at how that animation is getting applied to all of our spheres. So our operation is going to be squash and stretch. We can see that we're not going to be dealing with the x-axis, we're going to be dealing with the y-axis. And we've seen this before when we had our character. Now our pivot in y is going to be slightly below 0, so negative 0.2.
Okay.
And that's going to set our pivot just below the origin, so that when we stretch, we're going to start jumping up in the air, giving us that jumping appearance.
Now, as we squash, it's worth noting that we will start to penetrate through our bench, but you're not going to be able to.
Yeah, you're not going to be able
it.
to see. The majority of the sphere still sits above the bench, and the angle that we're going to be looking at, it doesn't look as if it's penetrating the bench. And the advantage that we get of having the pivot below 0 for when we're jumping up far outweighs the disadvantages we get from squashing through the bench.
That's right.
So that's a single sphere. If we bring our attention to the copied spheres, you're going to see, as Jason mentioned when we were over doing the introduction, that everyone gets the same animation applied. And this isn't good because we want a randomized, more natural feel rather than this uniform animation being applied. So we're going to stamp up a parameter to our strength so that we can control our strength based on unique IDs across this guy, so that it changes over time, and so we have our overall seed as we've seen on the whiteboard. So let's jump down to the copy and let's create the new stamped parameter. And that stamped parameter is going to be sphere num. So sphere num. And it's simply going to be the point number that we're copying to, so $PT. We're also going to need a few parameters up on our asset. For now, I'm going to create noise speed and noise seed, and then we'll create the others as we need them. So I'm going to right click on our bleachers asset, come down to type properties, that is off the bottom of the window there, and let's slightly resize this guy so he fits on the screen. I'm going to come over to the parameters tab. Inside our audience folder, I'm going to create a new folder for our audience animation. So let's put that inside our audience folder. I'm going to rename this to animation. And inside our animation folder, we're going to create all of our parameters that are relating to the noise expression. So to begin with, let's create our noise speed and noise seed, and they're both going to be float parameters. So we've got our noise speed, which I'll name as simply speed. And I'm going to lock this with a minimum of 0 and leave it unlocked at around 10. And then we're going to have our noise seed, which I'll label seed. And I'll leave this completely unlocked in terms of range.
Okay.
So if we accept these, we can now create our basic expression on our strength parameter. So over on the twist top for our audience squash and stretch, I'm going to bring up our strength parameter with Alt-E. And let's maximize this so we can see exactly what we're dealing with. So we're going to be creating an S-noise expression, and we can see that the S-noise expression takes in the 3 values as we discussed over on the whiteboard. Our first value is going to be our change in time, so we're going to take our frame number and multiply that by our noise speed. So let's take our frame number, which is $F, and multiply that by our noise speed parameter. The second value is going to be the unique ID that's different for every sphere, and that's our stamped parameter that we've already created. So stamp, it was over on the copy audience. The parameter was called sphere num, and let's default that to 0 in case something goes wrong. And finally, our overall seed is going to be that noise seed that we created up on the asset. That closes off our channel expression, and this closes off our S-noise expression. So if we accept this, we're now going to have a randomized animation that changes over time.
Let's jump back in there real quick.
Interesting. Noise speed is probably set so low that the $F is being multiplied by such a small value that we're not actually really changing. So let's grab our parameters. Indeed, noise speed is set to 0.
So, yeah, we're not actually moving through X.
And we can see as we change this, we're actually forcing a move through our X dimension because we've got 32 being multiplied by a larger and larger and larger value. And as we change our seed, we're also causing the move. And you can see we were saying about it being a smooth curve through this 3D noise. As we change these values, we're not getting popping and flickering. We can see everyone
interpolating smoothly.
Yeah, smoothly moving between basically interpolation values. So we've got our speed. So now if we play back over time, we'll see animation, which we have full control. If we stop, that's kind of really fast. If we were to slow this down, everyone would animate more slowly. But we don't have control over the maximum and minimum amplitude. Everyone is going to stretch up to a value of around 1.15 at the maximum and squash down to a negative 1.15 at the minimum. And we really want to have control over those values, so we're going to create our min-amp and max-amp parameters. So I'm going to right-click on our bleachers and come down to Type Properties, find our Audience Animation folder and create 2 new flow parameters. The first is going to be our min-amp, and the second is going to be our max-amp. And I'm going to lock both of these, we'll set a range for both of these between -5 and +5. I'm not going to lock them because obviously an artist may, for whatever reason, wish to boost these past these values. We'll set this to a range of -5 and +5 on both min-amp and max-amp. If we accept that and bring up our parameters, see we now have control over our minimum amplitude and maximum amplitude that we can set. So we need to take these into account in our expression by putting our current expression into a fit expression. So this is the expression we were creating on the strength for our squash and stretch. We're going to place this inside a fit expression. So this is our value. The old min is -1.15. The old max is 1.15. The new min is going to be our minimum amplitude parameter, so min amp. And the new max is going to be our maximum amplitude parameter, so max amp. Close off the channel expression, close off our fit expression. So if we accept this and play this back, we can see that the audience are still squashing and stretching. Now as we bring our attention to these parameters, let's set our minimum amplitude to 0, and you'll see that none of these guys squash past their original size. And we can take our maximum amplitude and we can increase that if we want, we could decrease that. If we set both of these to 0, we get no animation at all because the minimum and maximum are set to 0. 0 means no effect. As we start decreasing min amp, we're allowed to squash down, so we have full control over how much we squash down and how much we stretch up. So all that's left to do now is create our final parameter for our overall control. So I'm going to right click on our asset, come down to type properties, and again inside our audience animation folder I'm going to create a new float which I'm going to call overall control. And I'm going to lock this between a minimum value of 0 and a maximum value of 1, so 0 through 100%. And if we accept this, we can simply come into our existing expression on the strength parameter of our squash and stretch, and take all of our existing expression and multiply that by our overall control parameter. If we accept this, you can see with overall control set to 0, we're going to have absolutely no animation. If we bring up our parameters, and as we start increasing overall control, we're going to allow up to 100% of the animation. So if we were to set this to around 50, we should see that everything is subdued compared to what it would be at full strength.
So put it all the way down to about 0.15 or so. Yeah, right in there. Very subtle. They're just all kind of talking and getting excited.
Yeah, and then as we were to boost this, say, when our lead character dives off the diving board, then they're going to be really excited.
Yep, very nice. And with that, that wraps up this video. That's pretty much everything that we wanted to do. So thanks a lot, guys.